Hello everyone. So, let us continue our discussion on mechanics of solids. So, we are in lecture 3 of week 1. Now, if you recall, what we have studied till now is that if you have bar and if it is exposed to axial pull, then we can find out the stress intensity, that is P by A. Similarly, if we have a 2D body, the last class we considered the 3D element, but let us draw in 2D. So, there may be a case where stress occurs along the face, and obviously on the opposite face it acts in the reverse direction. So, this is a tau. In that case, we have another set of stresses acting on the other two plane. So, this is also tau, and we have proved that this stress and the one on the right hand face, they too are equal, right. So, the first example is a case of pure tension. That means only tensile force occurs. In this case, the second case, we have two dimensional body, and we can only see that the shear stresses are acting on the boundary of the body. So, this case is called the case of pure shear. Obviously, there may be a case where we have a combination of these two, and that anyway we will consider as we progress in this course. So, if we consider further the material behavior, and we have studied this behavior, what is to be noted here is the points marked by these black dots, right. And we have also explained what are the meanings of this. Today, what I am going to tell you is that this maximum stress is what we call, if you recall, the ultimate stress. So, this is sigma ultimate. Now, when you design a structure, you basically focus on this sigma ultimate, and another point is here, this is the yield point. So, sigma yp. Why? Because the moment the material crosses this sigma yp, obviously there will be a plastic deformation, and sigma ultimate is the maximum stress the material can withstand. Now, if I ask you to design the first structure, say this one, how you are going to solve the problem? Obviously, you first define the load P that this structure is going to carry. So, this is what we call the demand. Okay. We want the structure to withstand a force of P, right. Then as a designer, what we do, we propose first the cross section. Say this is D is the cross section. So, the moment we propose the cross section, we can actually estimate what is A, and because we know demand, we can estimate how much stress the material is going to face. Now, this stress is what we called applied stress, right. So, this is equal to P by A. Now, you can easily sense that the material which is having a ultimate strength marked by this point D should have sufficient strength to withstand the applied stress. That means, we must have a situation where sigma ultimate is more than sigma applied. Then at least what we can ensure that the material can safely withstand the applied stress. It will be greater than equal to, because when it is equal, then also the material can withstand, and beyond that point it is going to fail. So, definitely we will not think of that. So, we should have a material where sigma ultimate is more than sigma applied. But in design, what we do, we always underestimate this sigma ultimate. What does it mean? We have sigma ultimate from the material testing. So, if we take a sample that I have already discussed, so as per any standard, you take a sample and then in UTM you can actually develop this stress strain behavior of the material, and from that behavior you can identify what is the sigma ultimate. Then as a designer, what we do not design a structure to actually go up to this point. The reason is the structure will be safe, but once it reaches this sigma ultimate, obviously it will cross this point A and B, and therefore there will be a permanent deformation, and in some cases it may so happen that the structure is not usable at all. So, what we do? We underestimate this sigma ultimate. What we mean by underestimate? We apply a factor which reduces this sigma ultimate. So, a factor which is less than 1 obviously times sigma ultimate is what is our sigma applied. Okay. So, now normally we have a factor, say n, this is called factor of safety. Say n. Obviously, the modified equation will be sigma ultimate divided by n is equal to sigma applied. So, the designer pre-selects how much factor of safety we are going to apply, and then based on that we reduce the load carrying capacity of the material, and accordingly we design. In fact, as a designer you have the liberty, we sometimes take sigma yield point. So, instead of ultimate load, we can also select sigma yield point, and then divided by n is equal to sigma applied, depending upon the design requirement. So, this is not a design course, we will not go into the details of that, but the idea is that you first take a material, then test the material to find out sigma versus epsilon. Then from that you identify these points A, B, C and D. Then accordingly you set your design principles and factor of safety and reduce the stress level. For example, if we take this, say yield point is my reference point based on which we will design. So, what we will do, say a factor of safety of 2. So, if we consider say a factor of safety n equal to 2, that means this sigma yp divided by 2 is somewhere here, is basically the point up to which we will stress the structure. So, this is our say sigma d, this is the stress level we are going to design based on this factor of safety, right. But the main idea is in any design, whether it is structure 1 or structure 2, the first thing is the material should have sufficient strength to withstand the stress applied, and then B, obviously we cannot arbitrarily apply this factor of safety. There are certain guidelines based on another fact is that we also should consider the economy, because if we increase this factor of safety, obviously we can sense our structure will be more safer, but in that case we do not utilize the material property fully. Although these are not the aspects of our discussion in this course, but the fact is it all comes from the stress strain behavior of the material. And once we have a structure, we have to keep all this in mind when we actually solve a problem. So, let us consider a problem now. So, the problem 1 says we have a steel bar of diameter 30 millimeter, which is exposed to 50 kilonewton tensile force. Material is steel, you can note, and it is a bar, that means we have only tensile force. So, we have a bar and we apply a tensile force of 50 kilonewton. The diameter of the bar is 30 millimeter. Then the problem says find the stress intensity. So, our first task stress intensity, then strain, and finally, the elongation. What is given? The gauge length is 2.5 meter and the Young's modulus E is given. So, this is 210 giganewton per meter square. So, given capital L, that is the gauge length, is 2.5 meter. Then P is equal to 50 kilonewton and the diameter D is 30 millimeter. So, we can find out the cross sectional area A is equal to pi d square by 4. So, we can estimate that. So, it is pi by 4 into 30 whole square. So, this is equal to 706.85 millimeter square, which is equal to 706.85 into 10 to the power minus 6 meter square. So, the first thing we can calculate is stress intensity sigma, which is equal to P by A, and this is nothing but 50 into 10 to the power 3 divided by 706.85 into 10 to the power minus 6. and then it comes out 70.68 into 10 to the power 6 Newton per meter square, which means the stress is 70.68 mega Newton, because it is 10 to the power 6. So, mega Newton per meter square. Second part, strain, we know it is stress by Young's modulus. So, we have a stress of 70.68 into 10 to the power 6 Newton per meter square, and then we have 210 giganewton. So, into 10 to the power 9 Newton per meter square. Then if we solve it, we get 0.3366 into 10 to the power minus 3, and the strain is unitless. So, we have estimated strain. Now, this is a very small amount. Sometimes in field measurement, we express strain in microstrains. So, we can convert that, because in SI units those conversions are very simple. Third question is the elongation, delta L. Delta L is nothing but the strain times the gauge length, right. So, we have strain as 0.3366 into 10 to the power minus 3 times the gauge length. In our case, it is 2.5 meter, that in millimeter is 10 to the power 3. So, we have a elongation of 0.8424 millimeter. That solves the problem completely. Okay. Now, let us take a different problem, problem 2, where we will design the cross section. So, problem 2 says that we have a circular hollow steel column which is carrying an axial load of 250 ton. So, given P is 250 ton. Then the design restricts the outer diameter of the column to 300 millimeter. So, we have a circular column. So, this is a circular column, and it is hollow. And because it is a column, it actually carries a compressive force of 250 ton. The outer diameter is 300 millimeter. So, capital D is equal to 300 millimeter. And the problem says, if the ultimate stress of the material is 5000 kg per centimeter square. So, sigma ultimate is equal to 5000 kg per centimeter square. Find the thickness of the column for a factor of safety. So, factor of safety is given, it is 4. So, we are supposed to design the column. Our first task is to find out the internal diameter. So, this is D internal, and then once we find out D internal, we can find out what is the thickness of the column, that is the minimum thickness to be provided. so that the material can withstand the applied stress. Okay, so what is sigma allowable? This is sigma ultimate by 4 kg per centimeter square. Now, you see the difference between the previous problem and this one is that we restrict the material behavior with a factor of safety, and that varies from design to design. So, according to problem, our sigma allowable should be equal to sigma applied. So, that means we have 5000 divided by 4 should be equal to P by A. So, what is A? A is equal to pi by 4. We have outer diameter d square minus small d I n inner diameter. So, that is the cross sectional area. So, it is pi by 4. Because our stress is expressed in kg per centimeter square. So, we use the same unit, d is 300 millimeters. So, this is 30 square minus d I n square. Therefore, what we have is 5000 divided by 4 is equal to P, which is 250 ton. We have to express in consistent unit. So, it is kg per centimeter square, and then the expression of A is pi by 4 30 square minus d n square. Therefore, what we have is 30 square minus d n square is equal to 4 times 250 times 10 to the power 3 times another 4 will come from the denominator. So, we have pi times 5000, right. And then we can find out what is d I n. I give you the value of inner diameter directly, you can just work it out. So, it will be 25.41 centimeter. Now, this is the diameter, the inner diameter we have to provide. So, what is the thickness? Thickness is capital D minus d I n. So, it is 30 minus 25.41. So, which is equal to 4.59 centimeter. That means, we have to provide T minimum is equal to 4.59 centimeter. We will stop here in this course, but as you progress in design, you will see when you estimate this minimum thickness, anything more than that you can provide, because if the design requirement is say 4.59, obviously if I provide more, the structure will be safe. So, in design you will actually discuss different other factors, because if you as a designer propose 4.59 centimeter, it is very difficult to construct at site. Then we normally say T design will be equal to 5 centimeter, but we are not going into that domain. So, we will restrict ourselves here. So, our minimum thickness is 4.59 0.59 centimeter. Okay. So, here in this problem you can see how we apply a new concept called factor of safety. Let us take a different problem, problem number 3. It says a bar of length L has 3 different cross sections. So, you can see the total length of the bar is capital L. Now, it has 3 different cross sections with different diameter D1, D2 and D3, and the respective length of the sections are also given L1, L2, L3. We apply a tensile force of P, and the material constants for 3 different sections is E1, E2, E3. We are supposed to find out the net elongation of the bar. Now, you can see we apply a force of P over this bar, and the assumption is this P is acting uniformly over this entire cross sections. Okay, this is an assumption, and for the time being let us assume that. So, the same P is acting at 3 different internal segments. So, the first one, if I draw the free body diagram, we will have same P applied at both ends. So, the diameter is D1 and the length is L1. Now, for this case what we can do, A1 is the area, cross sectional area. So, this is pi D1 square by 4. Then we can find out what is sigma 1. Sigma 1 is equal to P by A, which is pi D1 square. 4 will go to the numerator. So, we have 4 P by pi D1 square. Now, once we define the stress, we know the material property, which is Young's modulus in this case. So, we have epsilon 1 is sigma 1 divided by E, actually E1. So, what we have is 4 P divided by pi D1 square E1. So, that is the net elongation, net strain applied in segment 1. So, this is the segment 1, segment 2, segment 3. So, what is net elongation? Del L1 is nothing but the strain times the gauge length, which is L1. So, we have 4 P L1 divided by pi D1 square E1. Similarly, we can find out the net elongation of segment 2, that is del L2, which is 4 P L2 divided by pi D2 square E2. And for the last segment, delta L3 is going to be 4 P L3 divided by pi D3 square E3. So, what is net elongation? Delta is equal to delta L1 plus delta L2 plus delta L3. So, what we have is 4 P L1 divided by pi D1 square E1 plus 4 P L2 divided by pi D2 square E2 plus 4 P L3 pi D3 square E3. So, you can simplify this, we have 4p by pi common. So, then we have L1 by d1 square E1 plus L2 divided by d2 square E2 plus L3 divided by d3 square E3. So, that is the expression we are looking at. So, we start with the fundamental definition of stress, uniform stress, and then we ultimately find out the elongation over a gauge length of capital L. That solves the problem. We will also provide you some list of problems that you please solve. If you have any doubt, you can raise your queries and then we will address it. So, with that, let us close our discussion in this lecture. Thank you very much.